It's exactly 2 o'clock, so we'll make a start. Good afternoon, ladies and gentlemen, and welcome to Innovation and Evolution, the Géant Backbone Network. I know there's a lot going on in and around TNC today, and so we appreciate you giving us your time and attention. There are 4 speakers for this session, more than the usual 3, and as such we have a lot of ground to cover, and it may be necessary to keep questions till the end. We'll see how we go. So without further ado, I'd like to invite Mark Johnston from Géant to come to the stage.
Thank you, Toby. Hello, good afternoon. I'm Mark Johnston. I lead the team that plans, builds, operates, and secures the Géant network. Innovation and evolution drives disruption in production environments. Innovation and evolution requires generally new software, new hardware, new ways of working, new processes, interoperation with other networks, and interoperation of the old with the new. These new things require certification that they are fit for purpose, and they need validation and verification that they're fit for use in production and in a production environment. I think as a community, we're at the beginning of potentially quite a lot of disruption with the introduction of new architectures, new technologies, and perhaps with the change we architect and deliver services. And we need to verify and assess and test whether those new technologies and new architectures deliver a benefit, and obviously assess how we would implement them, how we would interoperate them, and how we would migrate from the old to the new. So I'm going to talk about why I think these things need to be done in a production environment, why perhaps that is not a good idea, and why that can't actually be achieved. Then go through some thoughts that Géant Operation has on how we could achieve these things in a production environment. And then go through our thinking on next steps and some use cases. So I think if you take a lab, it's generally got a few sort of replica bits of kit from the network, maybe a few servers interconnected with some wires and fibers. Are they set up to interject millions of routes, thousands of flows? Are they integrated with other labs to create multi-domain environments? They generally are based on the technology that a single entity has in its network. So interoperating across multiple domains is perhaps not possible. And testing how perhaps new technology that you want to introduce, how that will then work with your partners. Labs aren't generally set up to do these things. Certainly labs, we all have networking labs, I'm sure. Do we have that lab fully integrated with people managing and dealing with large data sets, and how we can integrate those environments and deliver services effectively across those? Are we set up to do that in a lab environment? I don't think so. So therefore I think we have to take a different approach to how we're going to evaluate and figure out how we're going to migrate and introduce these new architectures, new technologies. Can we do that in a production environment? Perhaps not. We're delivering production-worthy services. Some of those are bound by contractual SLAs. All our production networks are going through continuous change to deliver new services, add new hardware, grow them, change them, adapt them based on the demands of users. That's controlled through maintenance windows, through change control. If we kind of then drive our innovation and evaluation of new technologies that way, clearly it would take a lot of time. Clearly innovation requires new software, new operating systems. We don't want to put those in a production environment until they've been fully evaluated, certified, and verified. And again, that interoperation across multiple domains, I think in a production environment is difficult. So I think what Géant Operations is thinking is there is a need. Yes, we need labs to certify things. to say, yes, they're fit for purpose. Then we need another environment to verify and validate things are fit for use. And we're looking at creating a network and operation verification capability. It's not just a bunch of hardware. It's much more than that. So it's looking at having simple things like an empty rack with power, connectivity, servers, plus those things integrated into alarm management, operational processes and procedures. So if somebody's got something they want to test, there's a way where they can incorporate that, integrate that quite quickly. And clearly, we want to do this in a multi-domain way. So we're looking for partners to help us develop this across multiple domains. So then we can start looking at how we'd work in a multi-domain environment, how we'd work with potentially different technologies and different vendors, different software. And the purpose of all of this, assessment and testing and verification of these new technologies in I guess, a more production-like way. So we can truly validate and probably make decisions on are we going to introduce SDN? Is there a real benefit in SDN? How can we assess it? Can we do that in a lab? Maybe, maybe not. We've got new infrastructures, applications. Clearly, all of this requires new systems, new tools for provisioning, for diagnostics, for management, reporting, monitoring. All of these have got to be developed and tested and verified. And then there's the whole operational methodologies of how we work. And then the migration. I don't think we're really thinking about the migration yet because we're still focused on the technology. So that is going to be quite an undertaking if we're going to do it without impacting users. So what is it? Clearly physical infrastructure. Clearly it's a whole bunch of different new technologies that hopefully we'll get from vendors. Hopefully some of it free of charge on loan so we can evaluate. Tools and applications that will then provide the surround of all of that. The network, so we need connectivity, people, software, and I guess whatever it needs to be. So, in terms of the next steps, there's resource allocated to this in the Giant project, to figuring out what we want to do with it, what's it for, design the capability it needs to have. We have GTS, clearly. We want to understand how we can leverage the capability of GTS in this environment. Obtain some partners to work with us, maybe donate some resources, some space, some technology. We need to then design this, determine how we're going to build, run, and support it, and then obviously understand the implementation and its cost, and then put a plan together to go and do it. So some thoughts on immediate use cases, implementation and operation of a software-defined network, the evaluation and migration of current connectivity services into software, internetworking of different SDN domains, interworking of current networks with a software-defined network. So clearly, we're not going to do everything in a big bang if we're going to move to SDN. So the two environments are going to have to interoperate together for a while. And then the whole how we do integration and virtualization at a scale, how that's going to work. And then, something that we've started to do there'll be talks later around alien waves and some of the things we're doing there. But clearly, we're looking to share infrastructure with the NRENs in a better way than perhaps we do currently, and then we need to test and evaluate that. Certainly as we go through SGA1 and then plans that we need to develop for SGA2 in the Giant project. And I'm sure there's lots of others, but these are our thoughts. And that's me. Thank you very much.
Now, despite my fears, we do actually have time, probably at this stage, for if anyone has a quick question for Mark, we can probably take that. If it's more along a sort of a longer question that might lead into a discussion, then I'll ask you to hold that back until the end of the session. So I'm just scanning the room now to see if there's... Oh, we do have, remember, a quick question from the gentleman on the edge there. Now, do we have a microphone nearby? Oh. They took me at my word earlier and figured they weren't going to be needed until the very end of the session. Yeah. Okay.
Now I have a mic.
So I think the question is, why not build a virtualized lab to do much of what's required rather than this physical one? Maybe, Mark, if you have a short answer now, give a short answer, please, and maybe we could pick up later.
But I think primarily, clearly, we need to introduce physical elements into it. So we need physical infrastructure to put those physical elements in. So I think it's a combination of both. But clearly, if we have new vendor technology to test and evaluate and want to do that in a more networking way, we need a physical environment to put that in and install it. And maybe we want to test how we actually implement that physically, because if it's new, we've never done it before, just install it in the rack may be a learning exercise.
Thank you for the question. Thank you, Mark. You may have noticed that the last bullet on Mark's slides there referred to interoperating more with NRENs. And so it's my great pleasure now to invite Peter Panis from Belnet to come to the stage and give a presentation on the optical aggregation layer that Belnet have developed.
Okay, thanks. Okay, thank you. Good afternoon. I'm working at Belnet, which is the Belgian NREN, working in the networks team. What I'm going to present today is the intelligent optical aggregation layer. So 2 years ago, we decided that we wanted to change our optical network, and I'm going to explain you what we did, why we did it, and how we did it. It might help you if you would want to update your optical network or your whole network in the future. My presentation might give you some ideas in your own decision-making process. So this was the network as it looked like until August 2014. The first reason why we really wanted to change the optical network, well, is a very simple reason. The optical layer was end of sales. So if we wanted to grow our network, of course, it's very difficult with a product that's end of sales. So we needed to change our platform. A second thing to mention is that above this optical layer, there's, of course, an IP layer, which is the interface to our customers. And this IP layer, so you see that the network is built in rings. These 4 rings, they come together, or 5 rings, they come together in Brussels. So Vilvoorde and Evere, these are 2 data centers in Brussels. And the reason for that is the IP layer, which is above it, was built in a star network, or is still built in a star network. So all these places, so we have Bruges, Antwerp, Geel, Arlon. So these have all access routers which were connected with a 10 gig wavelength towards Brussels, towards these 2 data centers, where there were co-routers located. This was a perfect setup when this network was built, because the initial initial demand of the universities, our customers, was internet connectivity. And internet connectivity typically was 100 meg or 1 gig those days. And they had to go to Brussels anyway, because that's where we made interconnection with the transit providers, or with the BNICs, for instance. So that was the initial purpose, that this network should be able to do this. Now, the other services that we have on our network are multi-points, layer 2, layer 3. And this can also be handled with this topology, with this star network. For this IP network is a star network. This can be perfectly handled with MPLS, because the core routers, they just handle the routing for one city to another city. It comes a little bit more difficult when these customers go to 10 gig. We can handle this with this 10 gig. So if Leuven, for instance, wants to have a 10 gig internet connectivity, we can do that by bringing a wavelength or a 10 gig lambda from Leuven to Brussels. But you need to install new lambdas, which is a little bit of work to be done. So it cannot be implemented in a few hours. So you have to go on site, plug in a transponder and so on. So that's a little bit of hassle. Especially if you go to a 10 gig multipoint, this network was really not fit to it anymore. And I'm not speaking yet about 100 gig demands, because this is really a pain for this kind of network, for the old network platform. So this is the reason why we went for a new optical network, but also for a new IP network. But we didn't want to do it with a big bang, so we wanted to do it in two stages. First, we wanted to change the optical network, and then a year later, the IP network. The reason for doing that is, well, it was quite urgent to change our optical network because, as I said, it was end of sales. And also, we wanted to really investigate what we wanted to have as a future optical network. We wanted to put enough energy in it so that the optical network can live for a long time and that it's fit for the future. Of course, the downside of first changing optical network and then the IP layer is that while changing the optical network, you need to have a vision of where you want to go to, because you don't want to end up with an optical network and then designing the IP network. And then I said, well, now I have this optical network, I want to do this and these things with the IP network, but it's not possible anymore because I'm stuck with this new optical network for the next 10 years, for instance. So you really need to create a vision. We needed, in our team, we really need to create a vision or a strategy, changing optical network where we want to go with our new IP network. Okay, for the optical network, so creating this vision, well, it had the reason for creating a vision is because when you build out an optical network, you have a lot of choices. I mean, at a certain moment when we started this project in 2012, I felt like a kid in a candy store. There were so many options, so many beautiful options, and it's quite nice because it's like you have like a bag of money and you can buy all this kind of nice sweets. But your bag of money is limited, so you need to make choices, and that also creates some stress, because if you pick that, you don't want to feel sorry later on that you didn't pick the other one. So it's like the paradox of choice. When you have a lot of choice, creates stress. And I wanted to get rid of the stress by bringing all the networks team together to say, okay, what are we going to do? What is going to be our strategy? Giving you an idea of all these choices, these nice sweets. You can go for a coherent network based on 40 gig lambdas, 100 gig lambdas. You have electronic dispersion compensation. You can go for colorless, directionless, contentionless, colorless, and directionless, and contentionless. Electrical GMPLS, optical GMPLS, all these kind of things. There's so many beautiful choices. I mean, the optical vendors, they worked hard the last years with coming out with all these beautiful choices. Now, when making the choices, of course, the new optical network needed to support our current services, which is 1 gig and 10 gig. And the second important thing is that need to be able to support 100 gig, which is obvious. And the other choices, they all needed to support well, it needed to take care that the future optical network was stable enough, resilient enough, that it was easy to operate, and it was future-proof. So where did we start? Because with all these choices, future-proof, which is an easy one. So the first choice that we made was, okay, let's go for a 100 gig network. 100 gig network, if you talk about 100 gig, then, of course, then you need to go to a 100 gig with coherent receivers, and these are perfectly fit to transport over a network without DCUs. So you actually don't need DCUs anymore. So this was the first choice that we made, 100 gig DCU-free, coherent, so I don't need to have dispersion compensation anymore, electronic or FBG or fiber brag grating things. You don't need to have that anymore. So okay, made these choices, but you still all have these other choices. What's next? The next important decision that we made is, okay, but if we're going for a 100 gig network and we keep on having a star network on IP layer, this would mean that we would have to change all these interfaces of this IP routers to all 100 gig, or bringing this 100 gig lines towards the core and having the core of the network in Brussels, there's 2 core nodes equipped with all these 100 gig interfaces or transponders, and also the core routers with 100 gig interfaces, which is quite costly. So we were wondering, is this really the most efficient choice to make? And also, if you concentrate all of this 100 gig in 2 data centers, I mean, it's putting a lot of eggs in one basket or in 2 baskets. And I will explain you later that you can come into troubles with that. So we said, okay, we don't want to bring everything to Brussels, so you don't want to have a centralized network anymore, we want to have a decentralized network. So that was the second choice that we made, decentralized. The advantage of doing that is that you increase the resiliency of the network, because if it's decentralized, what is the meaning of decentralized for us? Is that you don't have core routers and access routers anymore. Every router in the network can be an access router or a core router. That's the purpose. If you go for a decentralized network, you want to go from any POP to any POP in the most efficient way, not via Brussels anymore, so you need to create more mesh. So this was also a decision that we made. Let's go for a more mesh network, not talking about rings anymore, but a mesh network. But how do we make this decentralized network? Do we connect all these routers to each other with a dedicated 100 gig line, or do we create daisy chains? Not really ideal solutions, because then all the routers have a lot of IP pass-through traffic, which is not really ideal to me. So we came up with an idea that the best way is to go for an aggregation layer, and the best aggregation layer with proven technology is ODU switching. That was our idea, or that's still our idea. Going for ODU switching, it's different than before. Before we had a 10 gig wavelength network, and 10 gig services were directly coupled to 10 gig lambdas. Now with ODU switching, you can have a decoupling between the bandwidth that is provisioned on your network, which is 100 gigs, multiple 100 gigs, and the interface, which can be 1 gig, 10 gig, and so on. So having this flexibility on the technical point gives you flexibility on operating level also, because if you have a network, an aggregation layer that's built with ODU switching, you can remotely configure any service from any point in the network to another point in the network, as long as you have, of course, enough capacity in your 100 gig lines. Okay. Still, our choices have been reduced to flex grid and restoration, electrical GMPLS, and so on. How do we go to the next step? Well, audio switching is not is perfect. Well, it's not. It's very good because it's proven technology. Okay, another reason we wanted to go for audio switching is because we wanted to support 2 gigabit and 8 gigabit fiber channel, because this is in our product portfolio. And well, you need audio switching for that. You cannot do it with a packet-based only network. Talking about packets, so audio switching is not enough, because I said we want to have a decentralized network. We want to create, ideally, a full mesh that any router can talk to any router in our network without having to pass via another router. But if you have 32 POPs, then how many circuits do you need? It's 23 POPs, 23 multiplied by 22 divided by 2. You need a lot of lines. How much is it? Okay. So that's not really ideal. You can make it more ideal with a packet switch network. Beautiful thing of a packet switch network, and especially if it's integrated with audio switching in the same platform, the beautiful thing of packet switching network is that you decouple the client interface, which can be 1 gig and 10 gig, with the bandwidth that you reserve on your network. So you can have a customer connected on 10 gig from any point to any point on the network, on this optical network, but only reserving, let's say, 1 gigabit throughout on this line, or even less. So you have a much more granularity in your network. In our case, when we are going to packet switching, we will free up a lot of capacity because of this granularity that you have, which is a great thing. And that's what we call the intelligent optical aggregation layer, the combination of the audio switching and the packet switching. And this was what our RFP was based upon. There were some other choices that we need to make, and we quickly saw when we received the answers from the RFP that we can have also lambda switching at 50 gigahertz without a lot of extra costs. So we wanted to that also. Then there is restoration electrical GMPLS. That's something that we can always add on later with licenses. So that's not really a big issue. We can always do that later on. So this is the network that we finally built. As I said, full mesh network. And all of the fiber routes are coming into different data centers. So when I designed this, I needed to redesign the fiber layer, and we are quite resilient to any outage of a data center or a bankruptcy of a data center, because that's also something that happened during our process. Where are we now? We are at the stage of audio switching. In the next months, we have implemented packet switching, and we are moving now. We are going to move the audio switched circuits onto packet in the very near future, in the next months. And then, at the end of the year, we'll go to our new IP network to go for a fully decentralized network. Some figures, my last slide. during, okay, what are the most important figures here? Well, let's go to the last row because I'm running out of minutes, I think. In August, so in August last year, we moved the whole network from the old platform to the new platform, which is the Sienna platform, in 8 nights only. So there were 2 weeks. The migration only was in 2 weeks, when we went from the old network, old optical network, to the new optical network in only 8 nights. There were 0 complaints. The customers hardly noticed anything. So it was also. They were, of course, informed that there might be some interruption, but we were, thanks to the cooperation with Sienna and the plan that they made, we were really able to limit the outages to very minimum, so that we didn't have any complaints. The total project lasted for 2 years and 3 months, and that's included. So I'm only talking about the optical network, and the strategy for the IP network, but the IP network not being changed yet. And I predicted that it was going to be 2 years and 3 months 2 years ago, and finally we reached our deadline because we wanted to have everything migrated by August 2014, September 2014, which we did. So we thought it was a quite success. That's all I want to talk about. If there is any one question?
Yes, indeed. I was going to say, our speakers so far have been consummate professionals, and we do have time for almost a medium-sized question, I think, at this stage. So please, if anyone has a question.
I think it was very clear.
Indeed, it was very clear. I'll have just one quick question for you. So do you envisage that your next evolutionary step would be another redesign at some point in the future? And if so, how far are you looking ahead? How long do you think this design will last you for?
I think, well, the purpose is that this design will last for a lot of years. I mean, I think we get all the right building blocks. Okay, a future design can be that we go to 200 gig, 400 gig, and so on. We could potentially do that. If we have the need. But for the moment, there is no need yet. But I think that we have the right base to be sure for a few years that we have the perfect network.
Right. Thanks very much, Peter.
Thank you.
And our next speaker, and as I say, we're bang on time, we're doing very well, is Guy Roberts from Géant. Guy did confide to me at the start of this that he was a bit concerned that the screen was a little on the small side. So please bear with him.
Right. So I've got till 3. Till 3 o'clock.
You have until 3 o'clock.
Very good. Okay. So remote. Not seeing much. Huh? Ooh. So you can go back one slide, which is the up and down. Left and right. Aha. Good. Okay. So yes, thanks Toby for the introduction. So I'm Guy Roberts, and you probably, or many of you might know me from my other job, my non-day job, which is as co-chair of the NSI working group. But I'm not going to talk about that here. What I'm going to talk about is my day job, which is as the transport network architect within Géant. So I'm going to cover 3 topics briefly of things that I've been active in over the past 12 months or so. So I'm going to talk a little bit about the terabit trial that we've carried out in conjunction with Infinera. I'll talk about alien wave field trial. And lastly, I'll talk about the PXM card from Infinera and some of the things that we can do with that. And then Mian Usman will come and talk to you a little bit more about some applications for that. Okay, so terabit field trial. As you probably all know, our transmission platform within Géant is the Infinera DTNX, and it supports super channels of 500 gigabits per second, so that's 10 waves of 50 gigabits each. And Infinera, of course, are busy working on the next generation of that product, and they have produced a prototype terabit card, which we tried, had working in the network. And that happened last year, and so we're going to talk a little bit about that. But basically, it continues the 10 wave concept within the PIC. That's the photonic integrated circuit that they use. And they use advanced modulation schemes, which I'll talk a bit about, to bring the rate up from 500 gigabits to 1.7, up to 1.7 terabits per second, depending on the modulation scheme. And that was shown successfully working in our network. And this was a successful demonstration of 16 QAM in a photonic integrated circuit. So for those of you who managed to get to the WDM tutorial session by Jeff Bennett, which was excellent just before lunch, if you didn't go, I'd kind of recommend that you go and have a look at the slides for that, because Jeff gives a great presentation on that. I'm just going to touch on the different modulation schemes. So currently we have PMQPSK in our network. So that's polarization multiplex quadrature phase shift keying, in case you wanted to know. And that basically gives you 4 bits, 2 bits plus 2 polarizations. So it uses something called a super Mach Zehnder, which modulates both amplitude and phase to give you those 4 quadrants. And then what Infinera have done is they've developed the 16 QAM modulation technique, and that gives you a constellation of many more points with different phase and amplitude. But what you do see there, the key point about that diagram, as you go to these larger constellations, the size of the dot in each constellation shrinks right down. So effectively the dashed line is your power limit. You can't go beyond that power limit without getting into nonlinear power regime. So as the modulation scheme gives you a larger constellation, for the power limit that you've got less photons per bit. So what that means, in effect, is your reach reduces. So on the right here, you'll see that there is a trade-off. As you increase your modulation to more sophisticated, larger constellations, 16 QAM, the capacity, the C-band capacity will go down. Is that right? Sorry. The reach goes down and the capacity goes up. So you've got a reach capacity trade-off. So you get more reach with BPSK, but less capacity. If you want more capacity, you get less reach. So you can't always win with this. You either got to trade one or the other. But where the technology is moving is towards software configurable modulation schemes. So it allows you to trade off the modulation scheme to suit the particular fiber reach that you have. So if you want to get long distance, you'll use BPSK. If you want shorter distance, you need a lot of capacity. 16 QAM is a solution. So you can effectively dial up your modulation scheme to get the capacity that suits the fiber that you have. So, and there are some intermediate schemes as well available. So this was the trial we did. Just check the time. Right, so this is the trial that we did, and we ran it from Budapest to Bratislava, so 3 hops. So this is on our production system, and no laser. Okay, so what we did is we injected the light in the Budapest end. We ran it through. We had a loop back. We're monitoring it both remotely in Bratislava and then locally loop back in Budapest. So we can effectively had two sets of reaches. There's a 250 kilometer and a 500 kilometer reach. And then the signal was then captured using a digital oscilloscope. So that's the actual route that we used. And it was quite interesting. We were actually using the real network, and there was actually an interesting outcome of that. We discovered some interesting artifacts of sudden changes in polarization that were happening when lightning was hitting the fiber on that route. So just by carrying out the trial on the real network, we found interesting things going on. So these are the results. So in this case, we've got 16 QAM. That's 1.7 terabits. So the reach would only go one way, so that's 255 kilometers. But you can see the 10 waves there all have a Q factor, which is above the threshold required, which is 5.7-ish. And so you had a working system there. And then slowly the modulation schemes were dialed down, and as you did that, the margin improved. So here with 8 QAM, 1.3 terabits per second, lots of margin there. So you've got a good over 2 dB, maybe 3 dB of margin. And then further on, 21 gigabits using QPSK, 0.7 terabits at QPSK, and more margin again, 500 kilometers reach. And then BPSK, it ran entirely without any need for forward error correction. So all the other modes are all running error-free, but required forward error correction to operate correctly. So in summary, what did we get out of that? What we showed is that in a real system, terabit super channels are possible and working. The technology is there, and we're getting some good results. So I'd just like to thank Infinera, and they did want me to point out as well that when they move to production product, that the performance will improve further. Okay. So the next topic I'd like to mention is the alien wave field trial. So this is something that we've been doing over the past 6 months or so. So the alien wave field trial has been operating from Hamburg through to Amsterdam. So what are alien waves? Alien waves are light that's taken from a third-party equipment and then carried over the dark fiber system from another vendor. So in this case, we had light which was produced by the Infinera equipment, in this case the 10-wave super channel, and then carried over the Sienna equipment belonging to SurfNet. And so the good news is we've had excellent results, which I'll talk about. Before I launch into just describing that, I'll just talk about the economics of alien waves. So, that's really the motivation for this community, I believe, is to get a good result in terms of cost savings for us. So the basic principle is that where you've got parallel infrastructures which are not fully utilized, so fibers, say, from Amsterdam to Hamburg, one owned by SurfNet, one owned by Géant. If you can reduce the amount of fiber and share that fiber among all the NRENs and Géant, your fixed cost goes down, and eventually you will get to a point where you get a much better unit cost for each service. And so for us, this means that we've got three NRENs sharing that fiber now. We've got SurfNet, Nordinet, and Géant all serving using the one set of dark fiber. So the cost is reduced by 2/3 for us. So that's a good saving for Géant and therefore for the NRENs. Okay, that's just a picture of where the fiber goes, and stating what I've said, that, this is two lots of dark fiber infrastructure, which are effectively duplicating infrastructure for the community. This is what the field trial connection looked like. We have on the left and the right, in the grey area, that's the Infinera equipment. So the core of it is the OTN switch, which is the switch matrix there. And then we have the AOLMs, that's the photonic integrated circuits in there, so it's the super channel, 500 for 500 gigabits per second. In the field trial, what we did is we took 2 waves. We amplified them locally on an ATC shelf. We muxed them out, separated them out into 2 pairs of fibers in this case, and then injected those into the 6500 equipment from SurfNet, so Sienna equipment. Okay, and these are the results in terms of receive margin. So what I've plotted here is at the receiver at each end. So you've got Hamburg on the left, Amsterdam on the right, and then you've got the bit error rate in one axis, the vertical axis, and the horizontal axis you've got receive power. And the receive power that we receive is the bottom right-hand point there, and the margin shows how many dB receive margin is built in. So the system will fall over or start to run errors when it gets to about 10 to the minus 3 bit error rate. So it's an excellent receive margin. It's quite interesting to note that there's a bit of a curve on those lines, which indicates there's a noise floor. So that's what you would expect in a typical DWDM system. You can often, even if you increase the power, you may never remove all the bit error rates. So there'll be a little bit of background bit error that has to be corrected by forward error correction. But that's a normal expected. But as I say, with forward error correction turned on, you're getting operating with plenty of margin. So the next steps, are that this is going into production with a different variation of the setup. If you want to know more about alien waves, I'll talk a bit more about these results and the economics of those in a session tomorrow morning. So where are we going? We're moving into production, and we're also investigating options to do other alien waves in the network. Okay, so right, I think I've covered all that. It's working well. So my last topic is the PXM, which is the what's known as the packet TIM. So this is a layer 2 Ethernet switch in a blade in the DTNX equipment. What it is basically effectively a 200 gigabit switch. So you've got 100 gigabits Ethernet port facing the sort of client side, the front connector, and 100 gigabits out onto the back plane, which is then connected via OTN, goes through the OTN switch and can be sent out to any destination. And the switch includes a sort of MEF type service, so E-line, ELAN type services. So what's this good for? Why would we like to see a Ethernet switch on the edge? Well, it kind of moves our service from being just a transmission layer with built-in OTN into a kind of POTS realm. And that really allows us to do aggregation at the edge where we connect, say, an NREN customer or service into the transmission network. We can aggregate at layer 2 and forward it. But we can not just aggregating and forwarding, we can aggregate to different destinations. So there's a couple of different applications we have in mind, and I'll just touch on one briefly. In addition to that, the card is also effectively OpenFlow enabled. So there's the OTS, or Open Transport Switch concept, that Infinera have been working on in the ONF. So it's an extension to OpenFlow that brings in the transmission characteristics. And they basically use that as a northbound interface to their management system. So you can use that REST-based interface to request services between the edges of your network. Okay, so that ability just gives extra control over that network. So there's different ways we could use that. We could use it for creating things like layer 1, 0 VPNs. I don't know if you were in the session before lunch on WDM. Infinera touched on some of the applications, and I think Mian will talk about that as well. So you can give control to applications and users to control that layer 01 VPN. But the one I think was most likely to happen early on in our network is looking at router bypass applications. So by taking so if you've got Ethernet layer MPLS, or you've got in our case, routers which are interconnected via effectively daisy-chained in our network currently with 100 gigabits N by 10, 100 gigabit links, we can do router bypass. We can drop capacity off the network. And in this particular diagram refers to an experiment that was done in conjunction with ESNet and Infinera, where they built an application with an OpenFlow controller to detect flows, large flows, and redirect those off the packet layer onto the transport layer. So that's an example of the kind of application that can be delivered using an integrated OpenFlow interface on both the packet and transport layers. Okay, so in summary, we've been busy looking at new functionality, new technology in the transmission layer. The technology continues to evolve, so alien waves will help us cost down the network. The packet TIM brings new ability to both cost down and add new functionality to the network. So we've got a lot of new options there over the coming year. So thank you.
Thanks so much, Guy. I'm pleased to say that we've got quite a bit of time for questions. So if there are any questions out there, great. We've got one straight off at the back there.
Yep. I was just wondering what, for the 1.7 terabit test that was being undertaken, what type of glass was that light being shone through? And secondly, the kit at the end, what backplane does that have? Because 1.7 terabits pretty much wipes out my SUP 2T that I've got.
So not quite sure I caught the question. So you're basically saying for the 1.7 terabit, what kind of equipment was connected to it? So how was the data generated? I believe it was actually generated some test data, which was transmitted and then was captured in short bursts using a digital oscilloscope and then analyzed in software later. So this wasn't a live data stream. It was just checking that the optical transmission layer was operational. Does that answer the question? Okay.
Any more questions at this stage? Okay, well, we're doing really well, so I think there'll be some time at the end anyway for questions for any of the participants. So with that said, thanks very much indeed, Guy.
Thank you.
Thank you. And our next and final speaker this afternoon is Min Usman of Géant.
Thank you. Thank you, Toby. Is it working? My name is Mia Osman, and I work with Guy in the same team. He looks after the transport layer, and I'm the IP network architect. He talked about the past 12 months, what we have done, and I'm going to talk about what we plan to do in the next 12 months. So I'm just going to go over a little bit about the service architecture and how we see it in Giant Network. Some of the challenges that we see, Mark already touched on some of the challenges from operations point of view, so I'll talk about a little bit as well. SDN approach, maybe how we can solve some of the challenges with using SDN. White box switches, so I'll go into details on that, and service and IP trunks over Infinera Packet TIM. So Guy just talked about Packet TIM, and I'll talk about how we see it being used in Giant Network to optimize the IP trunks and make the utilization better. So first off, the network. Obviously, the services that we delivered are built on a network which is built on the infrastructure. The infrastructure consists of dark fiber, then we have DWDM network. On top of that, we run IP/MPLS network, which some of the trunks are leased capacity, some of this is running on the DWDM network, and on top of that, we run IP services, layer 2 VPN, layer 3 VPN, MDVPN, and multicast type of services. And along the line, you see operations. Obviously, they have to manage the network, the infrastructure, the services that we delivered. But at the end of the day, all the services, what the network is doing is it receives the packet, looks at the header, and then just sends it out. There is no intelligence that's in the network that it doesn't do based on the flows. So for example, all the application initiation is from end host, end to end. No application is created by the network. We just receive the packets and send it out. If there is a large flow, we don't have enough capacity, the packet is dropped. There is no intelligence built into the network which says, well, we don't have capacity here. Maybe we can route it via a longer way and send it there. So I'm going to talk a little bit about that in more details later on. So the network really is working on end-to-end principle. The end host starts and initiates the application. Just take it and send it out a different port. So the challenges we see is we do have quite a diverse service portfolio. Unlike the commercial service providers, we have a lot of multicast traffic. We have services like MDVPN running. So we have to try these new services, which means we have to try this new Junos operating system because we run Juniper on our IP layer. So what Mark touched on earlier was that we have to do a lot of type testing. We have to in order to try new services, we have to test new software. There's always drive to go to the next version of the software because some of the features are available in there. But the other side of that is that some of the new features are there, but some of the older features are not working in the new version. So we have to make sure that we do the testing. And this testing takes a lot of time because you want to make sure that the new features are working and the old ones are compatible with it. It's working fine. We do the type testing. Then it's rolled out in the network, which takes a couple of weeks. And by the time we finish, there is another feature that we want to try and test. So that's quite a challenge for us. It takes a lot of time. A lot of manpower from operation is spent on this work. Then we also have demanding big science users. They want high-performing and stable yet innovative networks. So the users like LHC, they not only just say, well, we want the network to be congestion-free, they also want to work with us and on the solutions for their applications. It's like bandwidth on demand. LHC1 is a very good example where the community worked together to build an overlay network across multiple service providers in the NREN community. So quite a demanding big science user. And then, of course, deliver services at competitive cost. I don't think anybody has come up to us and said, you're not charging us enough, please charge us more. So that's another challenge that we have to look at. We have to reduce the costs and make sure we are delivering services at a competitive rate. And then the other point is we are committed to long-term contracts and relationship with suppliers. What I mean by this is we have contracts with Juniper. We can't just say, well, Juniper doesn't support this feature, Infinera doesn't support this feature. We're going to switch them off and go to Cisco. We can't do that, or a vendor XYZ. But A, we are already locked into the contracts, and B, we need a lot of CapEx to do that, which isn't always available there. So we have to work within what we already have there. And I'll show a little bit about this vendor lock-in in the next few slides. So I just wanted to touch a little bit about the innovation in Giant. So I work in service activity and GRA2, the joint research activity. I was just thinking, when I was putting the slide deck together, how can I try and explain what service activity is and what joint research activity is? And I came across this wonderful kind of diagram from Cinetic model of cycling world. Basically, the service activity in Giant sits on the operational world of side, where we have rules, we have processes, we have procedures, and just like the commercial network, we have SLAs. So we cannot just try new things in the production network. We have these challenges. Mark already touched on some of those. On the other side, we have innovation world. That's where the joint research activities of Giant sit. And this is where the new things are tried, the new technologies are tested, experimented, and the developmental thinking happens there. And so what we are doing here is all the challenges that I mentioned, we're telling to GRAs that these are the challenges we have, what can you do to help us solve these? And they're looking at the operational requirements, do the testing, do the proof of concept, and hand it over to the service activities operations team to say, well, now you can go and pilot this in Giant network. And so this is the kind of way that we are working within Giant project. And a little bit more about what SA1 and GRA2 are doing, so because I'm involved in both SA1 and GRA2. Now, SA1 obviously is the operational world, and we are looking in SA1 world, we are looking at how we can solve some of the problems and challenges that we have now, working with the existing vendors, leveraging on the existing infrastructure that's already there. So we're going to, in SA1, carry out 2 studies. One is the Layer 1 infrastructure study. Alex Vanderhill from SurfNet is going to lead that, and we're going to look at what infrastructure already exists. So just like Guy had shown the alien wave between Hamburg and Amsterdam, we're going to see other infrastructure and try and find some of the common infrastructure and see if we can get rid of our fibers and leverage on the existing infrastructure from the RNE community. The second study that we're going to do is multi-domain end-to-end transit network. Rob Evans from JISC is going to lead that. And what we're going to do is we're going to look at the, again, existing fiber network, existing cross-border fibers, and Giant optical layer network. And end-to-ends are going to connect with each other, peer with each other, and provide transit to each other. So kind of trying to reduce the equipment that we need at layer 3 and just providing services at layer 1 and enabling end-to-end to just peer with each other and provide transit to each other. Some of the end-to-ends are already doing it. We want to see what are the operational complexity of that model. Can that be done at the larger scale, the pan-European scale? So this is the kind of goal of that. And then, of course, you're going to run several technology trials working with existing vendors, Infinera, Juniper. Some of the trials Guy already touched on. And so most of the trials we're working on are trying to improve the performance and cost efficiencies. And then at the end, we're going to create a Giant network evolution plan. So we have a plan on how we're going to evolve the Giant network based on the 2 studies I mentioned and the technology trials that we are doing. On the other hand, in GRA2, the joint research activity, the innovation world, we're looking at how we can leverage on this new and upcoming technologies and how we can evolve the existing Giant services into SDN-based connectivity services. And then we're also looking at doing a proof of concept for software-defined exchange points, SDN IP, and using the white label switches. So this is where we're not locked into vendors, and we're not waiting for vendors to upgrade their operating systems and things like that. Obviously, we're looking at SDN at optical layer. Guy just touched on that in a little bit. And then obviously, GRA2 is part of a Giant project, and it's not just looking at the Giant use cases. There are a lot of different studies that we are doing. So infrastructure and network as a service, for example, is working with the NRENs in Greece, in Ireland, and in Netherlands, because they have data centers. They want to provide their users with infrastructure and network as a service, so working with them and developing a solution, SDN-based solution there. And there's a lot of focus on network and campus, so improving the performance at the campus network. This is also very interesting for SA1, and we are actually thinking and looking at how we can leverage on the work that ESNet have done with Science DMZ and kind of deploy that model in Europe and use and deploy a couple of DTNs and try and help the campuses in Europe deploy the Science DMZ architecture. So this is something that we are looking at as well. Just going to go into details of some of this in the next few slides. So this is the giant network topology. And here, this is the diagram I took from tnc Compendium of 2013. This shows the existing fiber infrastructure of the NRENs. Now, the studies that we're going to do in SA1 that I mentioned before, we're going to look at these existing fibers that are already there and try and build a layer 1 infrastructure using alien waves, the cross-border fibers, and identify some of the pieces that are missing. So if you look at PT and ES, we already have cross-border fiber there, and in fact, Giant IP network uses that to build the trunks between the two nodes. But there is no fiber from ES to FR. So this layer 1 study is going to look at where this fiber ends and how long fiber we need to make that connection between ES and FR. So these are the sort of things that we'll look at in a layer 1 study, so we can reduce the fiber infrastructure that we have and leverage on the infrastructures that NRENs have built within their NREN. And the second study that I mentioned, the multi-domain transit network, will also use this data and look at the fibers that are already there and establish pairings between the NRENs in these countries and try and provide the transit to each other and see if they can, using this and giant optical network, kind of replicate some of the giant services that we offer. So I talked about a little bit a diverse service portfolio and how we have very demanding kind of services that we run. So we have to really look at the Juno softwares or whatever operating system that we are using and make sure that it is supporting all the services that we have, and it's not if we are trying and introduce a new service, it's not interrupting any of the existing services. As I said, it takes a lot of hard work, a lot of time, a lot of testing. So how can we use SDN approach to kind of solve that? So one thing that in JRA2 we are looking at is maybe kind of having a separate individual control planes or controllers for different services. For multicast, for example, we could have a separate layer running a multicast out of Junos, where we have what this gives us is it reduces our reliance on the vendor operating system. And of course, we don't have to spend that much time testing it, because what we are running on Juniper is just the normal IP and layer 2 stuff which everyone else is doing. So these are the things that we are looking at. It's something that we're going to do proof of concept, not deploy in the network in the next 12 months. The idea is to kind of test, see what we can do with it. And of course, we don't want to end up with like 20 different controllers because of the 20 different applications. So this is something we are also looking at. And again, I've shown this graph here for multicast because some of you might think, why would you need multicast? We actually do use multicast. We have a lot of traffic, multicast traffic. And up until November, it wasn't there, but UMEDSAT project, now we have a lot of multicast traffic, so we can't just switch it off. Again, the giant network topology. Now focusing on this like blue circle that's there. So what I'm trying to highlight here is the two nodes that we have, one in Vienna and one in Budapest, and you can see a lot of NRENs connected to it. And then we have a couple of our POPs, 1, 2, 3, 4, hanging off these two POPs. But the rest of the network is kind of built based on the physical fiber. A lot of traffic basically comes from Frankfurt and goes to Vienna and Budapest. The trunks here are not really used much. So what can we do in these POPs, these 4 POPs that I mentioned, which are hanging off, and the only thing that they have to do is these routers, decide if they want to send traffic to Vienna or to Budapest. There is probably only 2 or 3 10 gig used there. There isn't many endpoints connecting there, only 1 or 2. So Juniper's support contracts are up for renewal in next August. And this gives us an opportunity to look at the white box solution. Some of the white boxes, SDN-enabled boxes, which we can deploy in these POPs here, for example, and replace them with replace the Juniper MX with these white box solution. Even if initially it just supports VLAN, it's fine, but we want to know what the roadmap is. So in future, we can try and use those new innovative solutions and integrate them with our network. What this gives us is it reduces the maintenance and support costs, because obviously the Juniper maintenance and support cost is another thing that we're looking at and how we can reduce that. And on the other hand, the flip side is that we have some POPs where we have only few 10 gigs, but we also have some POPs where we have a lot of 100 gig connections, and we are actually running out of 100 gig ports or the Juniper chassis slots. So what we're going to do there is going to use, again, these white box solutions and have an aggregation switch, like this one here. Oh, my laser isn't working, but you see it, aggregation switch. Look at the flows, look at the net flow data, and see which end-runs or which interconnects are exchanging traffic, a lot of traffic with each other, and kind of drop them onto this aggregation switch and just have 100 gig up to the MX router or Juniper router. So obviously there is a solution. We could always put a second MX next to it, but this costs a lot. This uses a lot of power, a lot of rack space. So we want to try and find some solution, white box solution, where we can use them, deploy them, and use them as aggregation switches. We don't want just to do layer 2. We want a vendor where, in future we can do a lot of SDN stuff, potentially SDN IP, run SDN IP on it. Now I want to talk a little bit about the packet TIMs, how we plan to use packet TIM and Giant IP network. So this is the eastern ring here that we referred to. So you can see this big ring. This is following the physical fiber path. Now, a lot of traffic from Western Ring, which is this here, from Frankfurt, goes to Prague, goes to Bratislava, and then ends up in Vienna or Budapest, because we have a lot of connectors in Budapest and in Vienna. So a majority of the traffic in these trunks is not really destined or originated from these POPs. So we really need pass-throughs, direct pass-throughs, to optimize the trunk capacity. Otherwise, we end up with a lot of 100 gigs and just traffic going to Vienna and Budapest through those trunks. So looking more closely how this topology looks is basically we have already started some of the optimization work. That's why you see this whole ring is 100 gig except for this, which is 40 gig. So as I said before, this is following the fiber path, but majority of the traffic actually just goes from Frankfurt, or rather Western Ring goes to Vienna or Budapest, because that's where a lot of end runs are connected and the traffic goes there. So how do we want to optimize that? We can, with the existing technology in Infinera, we can do pass-through trunks, and we can have this 100 gig ring, a shorter 100 gig ring, as shown here, from Frankfurt, Geneva, Milan, Vienna, and then back to Frankfurt. So that's 100 gig, and then we can create 4 times 10 gigs between Budapest, Frankfurt, and Vienna. So this is what we can do today with Infinera. But the problem really is that we have this large flows, the elephant flows, which don't really work very well with n times 10 gig. So we're looking at solution where we can send larger flows as well. So you can see here as well, this traffic is in. So the bottom graph is our traffic from Google, very predictable. You can kind of see, well, it starts in the morning, goes up, peaks in the midday, and then starts going down. But the top 2 graphs are RNE traffic, and they're highly unpredictable. So you can see there's a 10 gig and a flow, and then here you can see more than 10 gig flow from CERN as well. So these are the kind of things that we have to deal with, the complexity that I was mentioning. So that's why we cannot just run n by 10 gig everywhere or create a full 100 gig mesh, because creating a full 100 gig mesh means that we're spending a lot of 100 gig interfaces and we're installing a lot of capacity and not using it. So what we want to do is, this is a packet temp. We are in the situation which is shown on the other side, which is low-speed circuit, n by 10 gig. If we go with n by 10 gig, then we have a lot of 10 gig going to different POPs. So for example, from Budapest, I showed we have 4 times 10 gig going to Vienna, 4 times 10 gig going to Frankfurt. But what we want to do is have a single 100 gig, and on that 100 gig, we say, well, 40 gig of that goes to Frankfurt and 40 gig of that goes to Vienna. What this gives us is, basically, it reduces the number of 10 gigs interfaces that we need. It reduces the flow limitation based on the 10 gig interfaces. Obviously, if we had n times 10 gig, we were limited to 10 gig flow. But using this, we're not really limited. Obviously, makes capacity planning much easier, and it reduces the number of slots that we need on the Juniper routers as well. So these red lines that I've shown here, these are the red lines that I've shown. These are the trunks that we could move to packet temp, and this is the plan. Once we've done the proof of concept, we'll do the pilot, and we'll try that in a couple of giant POPs in production and see how we can move some of the trunks onto the packet temp and use that. Obviously, it can also be used in our Western ring, where we have 100 gig ring right now. But end of this year, probably end of next year or middle of next year, we'll need to upgrade that. So instead of upgrading the 5 trunk links that we have in the network to 2 times 100 gig, we could use packet TIM and try to create a full mesh or within Western ring. So this reduces the number of interfaces that we need on Juniper. We're already running, quite running out of slots on Juniper. So this will give us a little bit of flexibility to work with on this with the existing stuff. So what this gives us is the capability to support this. So this, you can see, average less than 10 gig, and then suddenly we have this over 30 gigs of traffic. So we are able to support that. That's what we are looking for, and that's what we can do using this packet TIM. And I mentioned about the Western ring again. This is the Western ring where we can use the packet TIMs to upgrade the existing Western ring using packet TIM and reduce the number of 100 gigs that we need on the Juniper MXs. We can also use packet TIMs for a lot of other services that we have. So one of the service that we have is bandwidth on demand. So we can use that and move that service down to optical layer. And this provides the deterministic service as well, and moves the traffic down a layer. So once we move the traffic down a layer, we need less and less capacity on layer 3. So that also reduces some of the costs that we bear on Juniper. So if you can move the traffic down, we will try and do that with help of packet TIM. Obviously, some of the big science users who use overlay networks, so LHC1 is an overlay network on our IP layer. We can move that type of overlay networks down a layer again and move the traffic from layer 3 down to optical layer and reduce the number of interfaces that we need on Juniper. Again, if it kind of offers some sort of ELAN services, we can connect the end-runs at optical layer and enable them to peer with each other or peer through a root server. So they use just the optical layer to get the G and IP service without the need of the Juniper MX layer on top of it. Again, as Guy mentioned, it has the open flow interface as well to the DTNX, and we can obviously provide some of the applications that the big science users are looking at. For example, LHC1 working group. There's a working group which is looking at bandwidth on demand service, how the applications can talk to the network and see where the capacity is available. So using this, we can, using an API, we can enable the big science users to look at the network and kind of signal when they need the capacity and where they need the capacity. So this is something that we are also exploring. And of course, if we build the network on top of packet TIM and it's using the white box switches, which are SDN enabled as well, we envisage that maybe someday that SDN controller at the layer 2 will be able to talk to that SDN controller at the optical layer and signal when it needs more capacity on one link and less capacity on the other link. So it could, you could envisage it saying that the layer 2 is telling the optical layer that it needs less capacity on link A, but more capacity on link B, and optical layer just kind of going there and changing the, reconfiguring the trunk link. So this is something that we want to look at in future. Right now, we are kind of looking at individual, very small use cases, but we want to integrate these together, correlate these use cases, and make kind of build the intelligence in the network, both in optical layer and in the IP layer or the layer 2. So we're going to do field trial in this year. We'll move some of the IP trunks across. First, obviously, we'll do proof of concept testing in the lab, and then we will do a pilot. We'll move some of the trunk links from Eastern Ring, as I've shown, once we have a successful testing, and we'll move those in there. And then we'll start exploring the idea of using some of the OpenFlow features or SDN features in the optical layer, like that. So for testing, I just wanted to say a little bit about the lab we have right now, what we are doing. So Mark touched on the type testing. So what we have in lab, what we use in lab is this. We have 3 Juniper MX80s. We have a Juniper MX960, M120. We have 2 of PK8 switches and 2 of Dell switches running Cumulus Linux. We also have a couple of servers for the VM, so we can run different controllers, run the hosts, and test those. And we are working with vendors to test new products as PacketTim, and also looking at other vendors who are doing the switches, OpenFlow-enabled switches or SDN-enabled switches. Well, to summarize, we're trying to optimize the layer 3 and try and introduce a direct pass-through using PacketTims. And obviously, this kind of removes some of the routers we need in some of the POPs as well. As I said, we're looking at white box solution. We want to reduce the routers where we have only 3 or 4 ports used with the white box solution. That's what we are doing. More services and traffic down a layer. Again, as I said, we could move some of the services onto the PacketTim on a PXM card from Juniper layer. This will kind of reduce the amount of traffic on layer 3 and put us on layer 1 again, reducing our cost because the traffic is staying down a layer. And obviously, we want to make use of SDN and advanced path computation to build the intelligence on the network. As I said, we want to build intelligence in the network at optical layer using the PacketTims and the OpenFlow extension to it using APIs. And in layer 2 or layer 3, we want to use the white box switches, but the intelligent controllers and use them to build some sort of intelligence in both optical and IP layer. And that's it from me. Thank you. All right.
We now have plenty of time for questions, both for Mian and indeed any of the other speakers we've had this afternoon. So I'll go straight away. I think that's Xavier, is it? Yes.
Sorry. I have a question for Mian. It's about the concept of DMZ. I really not really understood this concept, so maybe it's due to this, but for me the idea was just to put some storage outside of your firewall, and that's all. So instead of pushing this concept, we have the perfect tools, perfect services to provide the same services thanks to MDVPN, and so you will have exactly the same usage and more security. So this is my comment.
Yep, so you're right. So this is what you've described is what Science TMZ is, and you can use MDVPN to kind of talk to one side and go to other side. But what I was saying within SA1, what we're looking at is kind of deploying some of the data transfer nodes that ESNet have kind of worked on and leverage on their work and put them in Giant Network. So not only do we provide the connectivity, we also provide enable the sites to test their machines and do the transfer with highly tuned nodes which are hosted in Giant. So this is more for testing purposes, but also to kind of maybe give more information. This is kind of going back to the campuses and giving them more information on science DMZ and try and rolling that architecture in big science users and large tier 1s and tier 2s for LHC. They could use, again, Giant IP, bandwidth on demand, or MDVP, and that doesn't really matter then. Any other questions? I guess everybody wants coffee. Oh, there's Jerry. You can ask question on coffee, Jerry.
So Mian, I got a question. It sounds like what all the packet TIM stuff is really just layer 2 pass-through, layer 2 transit under the IP layer. We have BOD, we have open exchanges that can do that kind of layer 2 transit between networks and offload the Giant network or the IP service. Why are we creating this complex array of new technology that can do stuff that we've had the capability of doing in the past?
Okay, thanks for that, Jerry. But basically, the exchange points you mentioned, they are not networks. So they're individual facilities. I understand they're exchange point, and we do connect to exchange point. We do peer with them. What we are talking about here is currently we have fixed 100 gig trunks across network. We want to change that, and we want to use that single 100 gig and go to multiple locations so we can reduce the number of 100 gigs we need at the IP layer. That's what we are trying to do with the packet TIMs, basically. So make use of a single interface, 100 gig, going into, for example, Vienna, and then send 30 gig to Milan, 30 gig to Geneva, 40 gig to Frankfurt. That's what we are talking about here. That's what we want to do. Basically, it is to reduce the cost of running the IP network that we are operating. Okay.
I'm not entirely sure you've convinced Jerry, but...
I can never convince Jerry.
Have we any more questions for me or any of the speakers this afternoon?
Nope.
No hands are going up at the moment. So we've done very well for time. Okay, so thank you very much, Mian. I think one... just a few notices for you. Firstly, your feedback. Your feedback helps us to improve each TNC. So please use the online feedback form or the app to provide your feedback on this and all the sessions. The gala dinner is tonight. Buses will depart from the pier side of the venue from 1915. I think there will be several buses from that time, so you don't have to be here bang on 1915, but you won't want to leave it too late. The shuttle buses schedule at the end of the evening was as per the email that was sent out. I had a quick look earlier, and it seemed to me that the first shuttle buses came back at 2200, and then every half hour after that, going on 3 routes, covering most, if not all, of the hotels that we use. So do please just have a look at that email, click on through, and you'll see. Or speak to the people at the registration information desk. They'll also be able to help. Tomorrow morning, remember that starts 30 minutes later than normal, and there will be coffee and tea. There is a presidential car museum on the first floor, and we can all visit it for free. Demonstrations. These run in every break area, or every break in the demo area, and check the online schedule so that you can see. And on a similar note, the posters, which are on display in the exhibition area, the presenters would be present with their posters during this coffee break coming up now, and they'll be happy to talk to you. I warn you, it does mean that you have to walk past the coffee and the biscuits, something which I personally haven't managed yet. So thanks very much indeed for your time and attention this afternoon.